Okay, today we are going to be talking about exponential functions. For this entire school year, we have been doing linear functions, where the things we graph. Remember when we did all the graphing that you guys really did not like, and we graphed lines, correct? Now we're going to look at exponential functions. What an exponential function is. This is the form of an exponential function. It is in the form y equals, and I need you to actually cross this out. I need to fix that. This should actually be y equals a times b to the x. I forgot to put that little a in there. So this is the function. This is this normal form of an exponential function, where a is a non-zero, so a can't be 0. B is greater than 0 and not equal to 1, and x is a real number. Examples of exponential functions would be like this. Y equals 0.5 times 2 to the x. Or negative 2 times 0.5 to the x power. These are all exponential functions. And we're going to see kind of what these things look like on a graph at the end of the notes. But right now we're going to talk about evaluating. Remember when we used to make XY tables for graphing lines? We're going to do that again for this. Okay? So what we're going to do, it says to evaluate the exponential function 3x for x equaling 2, 3, and 4. So we're going to have an x and a y. I hear music and I shouldn't, so whoever's music it is I hear, turn it off please. And let's close our laptop lids as well. Thank you. Yes. Yes. Okay. So we're going to plug in 2, 3, and 4. We're going to plug in 2, 3, and 4 separately. So first let's start with 2. So we're going to plug into the function y equals 3 to the x power. We're going to plug a 2 in for x. So that's going to give us y equals 3 to the second power. What is that? 9. Okay, now let's do 3. So we're going to get y equals 3 to the third power. What do we get there? 3 times 3 is 9. 9 times 3 is 27. So we get 27 when we plug 3 in. Okay, when we plug a 4 in, we get y equals 3 to the fourth power, which is 81. You see how that grew quite a bit there? 9, 27, and then 81. Whereas the linear functions, it was constant. It was consistent, a consistent shift. This is like exponential functions are when things either grow really, really, really fast or they decay really, really, really fast. So we're going to be talking about exponential growth and decay tomorrow. But for right now, I'm just introducing them. Okay, so on this example, in example 2, let's look at that one. So suppose we have 2 mice that live in a barn. That's where I got the rabbit example a while ago. 2 mice live in a barn. The number of mice quadruples every 3 months. Oh. The function f of x equals 2 times 4 to the x power models this situation. How many mice will be in the barn after 2 years? Okay, after 2 years. Okay, so let's look at this. Our equation, our function is y equals 2 times 4 to the x power. Now, in a function, I want you to write this down. With the general function, a equals a times b to the x power. Your a represents the starting value. Okay. B equals your growth rate. And that is how they came up with this equation right here. If you look, 2 is our starting value. That means we started with 2 mice. Our growth rate is 4 for every 3 months. And then x is going to represent your time. x is going to be where we plug in the values and stuff. Now, let's be careful with this one because if you notice, it says it quadruples every 3 months, and it asks after 2 years how many mice. How many sets of 3 months are there in 2 years? There are 8, right? So we're not going to plug in 2 here. We're not going to plug 2 in here. We're going to plug 8. Okay? So it's going to be y equals 2 times 4 to the 8th power. It's going to be a big number, yes. All right, someone put it in your calculator. What is 4 to the 8th mean?
16 times 16.
It'd be
65,000.
1,000,000.
Yeah. What is it?
65,536.
65,536. Oops.
Times
536. Now multiply that by 2, and that will be how many mice will be in the barn? 131,072.
Why did we do it times 2?
Because it was in the formula. See, we had 2 times 4 to the 8th. We did 4 to the 8th. That gave us 65,536. And then we multiply 65,536 times 2, which will give us 131.72 mice. That's a lot of mice.
No, it's not.
Suppose 2 mice live in a barn. The number of mice quadruples every 3 months. Can you imagine that? The function f of x equals 2 times 4 to the x power models the situation. How many mice will be in the barn after 2 years? The exponent in these exponential equations, with exponential growth and decay, the exponent is always measured in time. It's always kind of your time. So what we're going to do then is we're going to plug 2 in for this function. So we're going to do f of 2 equals 2 times 4 to the 2nd power, because it's after 2 years. Now remember, we don't do anything with the f of the 2. That's all that's saying is it's a function, and we're going to plug 2 in. So you don't need to worry. We don't have to even do anything with this. We just have to do this side. We have to simplify this side. We need to follow order of operations. What operation do we need to perform first? The exponent, correct? So we're going to take 4 squared. What is 4 squared? Times 16. So we get f of 2 equals 16 times 2 is that 32. So there are 32 mice after 2 years. If you have just 2, you start with 2. Then after 2 years, you will end up with 32 mice. Absolutely it is, yes. That's all it is, yeah.
What is it?
So, yep. That's how you find out. That's how you, basically on these problems, it's going to give you a number to plug in. And you're going to plug it in, find out what it is, and that will be your answer. We'll talk more about how they came up with this 2 times 4 to the x tomorrow's notes. Those are tomorrow's notes. Okay. Example 3. The function f of x equals 1.25 times to the x power models the increase in size of an image being copied over and over again at 125% on a photocopier. Graph the function. So what we're going to do is we're going to create an XY table to graph with. We're going to start with -1. We're going to do -1, 0, 1, 2, and 3. Okay, we're going to do -1, 0, 1, 2, and 3. So we're going to plug -1 into 1.25. So if our function is this, f of x equals 1.25 to the x power. So if we plug in -1, we're going to get f of -1 equals 1.25 to the -1 power. What do we do with negative exponents? What does this turn into? How do we change that negative exponent? Reciprocal, yeah, we got to take this and move it to the bottom. So this becomes 1 over 1.25. What's 1 divided by 1.25? 0.8. So this is 0.8. What happens if we plug 0 in? If we get 1.25 to the 0 power, you get 1. Okay. All right. If we plug 1 in, we get 1.25 to the 1 power. What does that equal? 1.25. Okay, let's plug in 2. 1.25 squared. What do we get? 2.5. Oh, you don't know, did you?
I was just saying something.
Oh, well, guys, let's use our calculators. Give me some numbers here.
Calculator? Yeah.
1.5625. You mean 2, wait, what is it? Is that right?
Yes.
Okay. 1.5625. Yeah, that's fine. 1.56. Okay, and then 1.25 to the 3rd power. What is that? So we'll say 1.93.
Yeah.
Oh, 95. 1.95. Okay. So now we're going to go ahead and make a graph using this. So here's our graph right here. Our first coordinate point is -1 and 0.8. So we go -1 and then up to 0.8. That's going to be about right there. Okay, we're going to put all of these points on our coordinate plane now. So this point right here is -1, 0.8. And then we're going to go 0, 1. 0, 1. 1 and 1.25, so we go 1 and then 1.25. That's going to go up a little bit more. Then we have 2 and 1.56. And then 3 and 1.95. It curves. It's kind of hard to tell in this. It almost looks like a line. I wish I should have spread out my graph a little bit, but it's going to look kind of like this.
Is this supposed to be like a rainbow?
Huh?
Rainbow.
It's going to be a curve like that, and that's what a lot of the exponential functions look. Thank you for listening.